forward, down to the right, like forward. Slowly, we're almost there.
Your hands on the...
In the back. I have to come from the back to rest. Okay, I touch it. I feel it. Yeah, I mean with the back of the hand. You can feel it. Put your hand. You can feel it. You feel it. You can see the hands deforming, and you can feel it. It's amazing. You see it, and you are able to feel the contact. That was really, really incredible to experience. What is happening is we still have our old habits. And our old habits is that we are used to program robot joints to create trajectories, synchronize these trajectories to move. And this is not the natural way of controlling robots. So we need to take advantage of the new capabilities that is being offered to us. All this journey, I feel I'm still doing my PhD in robotics.
In this podcast, I'm sharing my passion and curiosity for soft robotics, where we share inspiring stories about the work we do and how we can push the limit. I am Mara Dwini, and this is Soft Robotics Podcast. Support for this show comes from Science Robotics Journal. I really find Science Robotics to be a great resource for reliable and tangible research where we can really push the limit of the science we do in robotics. Great way to stay up to date with the published article is checking out the released monthly issue. All the links will be included in each episode description. We will also happen to have a regular conversation on the most published science robotic articles, where also you can contribute with your question and thoughts about the research. Thanks Science Robotics for sponsoring Soft Robotics Podcast. Hello, Professor Oussama. Such an honor to have you here in the podcast.
It is pleasure to be with you, Marwa. Thank you.
Thank you. So maybe I can go firstly for the recent expedition. I think if you can share about the OceanOne story, and now you have been returned from expedition, and I think that will be the scope for today, sharing this news. But can you tell us briefly the story behind OceanOne? I think 5 or 6 years ago started, and the iteration for people listening.
Well, this was an incredible undertaking because taking a robot to the sea is one thing. That is, we have developed in robotics a lot of rovers that can dive, and then they can see. So with the cameras, they can go around shipwrecks or structures underwater and monitor and bring images. The challenge we set for was to create a robot that can not only see but also can do. That is a robot that is capable of interacting with the underwater environment, which means that we needed to have hands, and to carry the hands you need arms, and to see the hands you need a head. And basically we ended up with a sort of an avatar of a diver. And building a robot like this that can go deep in the water is very, very challenging. But I can tell you, we did it.
Yeah, absolutely. Maybe because I know when 6 years ago, it was fascinating to see the iteration, and now it go, I think you mentioned deeper than 9 meter. No,
if you can share the footage, I think that's something we excited the recent expedition. That I think would be interesting if you can share the videos, and I know you will be interesting that to show us what you did in the recent expedition in France.
Yeah, absolutely. I would be happy to, and I'm going to share with all of you a little bit of that story. So, first of all, let me remind you that this is a robot that was designed to create a connection with the human. So without the human, the robot is not going to be able to accomplish complex tasks. And in fact, this robot that you see here on this image is the second generation of OceanOne. We call it OceanOne K, and the K stands for kilometer. So you can see here the robot concept with arms, hands, head, and this robot recently went to the Mediterranean and was deployed to dive on aircraft, submarines, and going deeper and deeper to an incredible shipwrecks, and then continued all the way to the bottom of the sea, nearly reaching 1,000 meters, which is really remarkable for a robot like this. So the original OceanOne was designed actually to go to only about 200 meters. And the design involved the concept of flotation that requires foam. And because we have arms, we needed to have oil-filled arms and links. So you have a lot of technology dealing with how we can keep the pressure inside the arms equal to the pressure outside. And OceanOne went to La Lune, as you know, in 2016. La Lune is a vessel of King Louis XIV sunk off the coast of France in 1664. And this boat was sitting there until 1993. Many, many years and centuries later, it was discovered. The way archaeologists will reach it is using this suit, which is very difficult to go inside because it's confined. And in order to interact, you have these very simple gripper. It's very, very difficult interaction, whereas divers, archaeologists needs to touch and feel and interact with those artifacts in much more dexterous ways. So we designed this robot to be sort of a combination of mobility, manipulation, sensing, vision, and this robot involved a lot of sensors. It is very complex system, but finally we can also talk about the fact that this robot had to sustain the pressure, and that meant a lot of new ideas in the design of the actuation, the hands. And the key aspect of the design is that when the robot is docking on any location, you can see the body of the robot still moving. And there is this coordination between macro mini dynamic system that allow us to take advantage of the fast dynamics of the arms to stabilize the system and reach and make contact without breaking, exerting large forces. So OceanOne is here. That is the original one that was in the pool of Stanford. And most of the early development went through haptic interaction that involves simulation, dynamic simulation of the robot. So you can feel the objects that you are holding and lifting. And in fact, when visitors come to my lab, this was the highest point of the demos, because you wear these glasses, you see in 3D, and you are able to interact with those environments through your hands and through your eyes. And everyone was able to do it, even a little child. This was easy because of the way this interface was designed. There is a lot of dynamics. This is the dynamic reflected at the hands. And when the hands is extended, the dynamics becomes large. The effective masses at interaction becomes very important. So we had to make sure that we take postures that are reflecting lower masses at contact. And when you combine two hands to hold an object, again, you change the dynamics. So the dynamics now, we call it the augmented object dynamics that allow us to control the robot properly. So the robot was deployed at the sea on the André Malraux, and you can here see an image of the robot between these two cannons of La Lune, and you can see also the haptic device with which we interact. So the haptic device, the two haptic devices allow us to touch the hands. So when the hands make contact, we feel it in the haptic device, but also to guide the robot when needed. And also we have the stereo that allow us to see. What happened actually immediately after maneuvering around these two cannons, the robot got caught. In fact, there was a current and the robot was stuck between these two cannons. And I remember it was midnight, the captain was saying, we have to leave, we have to leave. I said, what? We cannot leave the robot there. And here you can see the importance of connecting the human. So what do? You try to basically to actuate the thrusters to move back, but that didn't work. The only way we managed to bring the robot back was using the haptic device and using the arms of the robot to push the robots from this cannon. And the robot was rescued, in fact, and we recovered some treasure that we brought to the surface. And the archaeologists were very, very happy about it because this was untouched, unscratched Catalan vase from centuries ago that came back to the surface with the history of the sea written on it. So let me just show you a very short video of that expedition, the early expedition, before talking about the new robot. And in here, we are in the control room, and we are diving to the 91 meters where the robot is. And the robot is going to reach this area where you have the two cannons. You can see it here arriving. And as the robot starts maneuvering, as I said, we had this current that pushed the robot between the two cannons. And then the robot was completely stuck, as you will see it in a second. So you see the first cannon was hit, and then the robot went between the two. And you can see the thrusters rotating without any motion. So with the haptic device, we were able to push against the cannon. I mean, you can see the students' fear. And finally, fortunately, with the intervention of the haptic device, we were able to release the robot and rescue it and bring it back to the surface. The weather was really bad. We were not able to go back until a few days later. And then a few days later, we went back and located the artifact, this vase that we brought. And it was a very, very amazing, exciting moment. I'm going just to show you that moment when we grasp you can see it here between the two hands. And now we have to place it in the container. And approaching the container, making sure the position is correct where we are going to release it. And then once you close the container, that's it, because I'm going to put the sound for a second to show you the excitement. So this was an amazing moment after all of that work that went on. Now, I really want to talk about OceanOne-K, and OceanOne and OceanOne-K didn't come out of the blue. They came from a lot of development we pursued over the years with different robots. One of the first was Romeo and Juliet. Let me show you a little bit of Romeo and Juliet interacting with the environment and performing all kind of tasks. This was in the mid-90s. And ironing, vacuuming, two robots interacting compliantly, being guided, even moving and dancing. And then all of that went to another robot, Asimo, that stayed at Stanford for many years. And then we applied this to human motion. And all of this, in fact, led us to basically bring those capabilities to OceanOne. I just wanted to mention at the Pinakothek in Munich, we have now an exhibit of Juliet at the design museum there, and it is very exciting to see it with the videos and all the things that they have prepared. So, as I said, collaboration is very important and it can be done directly. So here the wrist sensors allowing the human to guide the robot, where in here we are using the haptics, and through haptics we are able also to interact with the robot and feel what the robot is touching. So the other problem, or one of the major problem building OceanOne-K, was how we build the flotation, because we cannot just go with the same material and increase the density, because the volume will be bigger and then heavier, and all of that makes the robot huge. So we found a new technology for foam design, which is based on hollow glass microspheres. And these are amazingly strong, so that you are able to go to 1,000 meters, but without the weight. And the robot, as you can see, became similar to the previous robot, a little bit heavier, but now the robot is capable of going to 1,000 meters. The other thing I wanted to mention is this compensator that is connected to the tubing that goes inside the arm. And these arms are filled with oil so that the pressure inside is equal to the pressure outside. But at 1,000 meters, you have electronics. And all that electronics need to sustain the pressure. So we had to change all the electronics to make sure that oscillators can be still functioning. So we went to solid state oscillators and all kind of things for capacitors and all the electronics to make it capable of going to the sea. So let me show you this short video about how the robot was tested in the pool. And here you can see the robot moving, you see the haptic devices, and you see how the robot can see through its eyes stereo, and this is reflected through the interface to the human. So in here, we see the stereo, the two images coming from the cameras on the eyes of the robot. And the robot was learning how to grasp object. Even if you miss it, the robot keeps moving and get these objects. And the robot was learning a lot of other things about how to interact with divers, or interact with two arms, manipulation, and use tools and all of that. And all of that in preparation of the mission in the Mediterranean. So the mission started in September of last year, and we went to Marseille, and then we wanted to continue to Corsica. This was done in collaboration with our colleague at DRASM, Michel Lour, who was the director of DRASM from the Ministry of Culture, and we aim to go to slowly from 40 meters on the P-38. P-38 is one of those very famous aircraft during the World War II, and Saint-Exupéry was flying one of those. Then we went deeper to 124 meters on Le Proté, which is a submarine that also was lost during the Second World War. And the plan was to continue to Aleria in Corsica to reach a second century Roman boat. It has beautiful oil lamps, and this is an area that is amazing, but it's very deep at 350 meters. Then later we wanted to go to 500 meters to reach Le Francisco Crispi, which is a magnificent boat that also was lost during that Second World War. And it has amazing, amazing biology, marine biology with white corals, very rare, that biologists would like to get their hands on, but it's very difficult to reach, and it's very difficult even to collect because they are very fragile and you can break them as soon as you touch them. So we continued the preparation of the robot at Stanford, and we were working on precise grasping. We were working on getting the robot to maneuver with a pole at the end of which you can have a scanner, you can have cameras and light, and we built those with the flotation so that we can film inside enclosures that are difficult to reach. So finally the robot arrived to La Ciotat, and here is the new boat, Alfred Merlin, that was used in that expedition, and the robot about to dive. I have to say, you cannot just go with one robot because you need to film the robot, you need to bring power to the robot. Batteries are not powerful enough to keep the robot going for hours. So we need to bring that power with a tether. And here is the control room. You can see we are all wearing glasses to see in stereo. And we are looking through the eyes of the robot, and we are connecting these haptic devices to touch the hand of the robots so that we can operate. And in fact, we had also a collaboration with the University of Pisa, the group of Antonio Bicchi, who developed these under-actuated hands. You can see the 5-finger hands that were used, and we will see them in a little bit. So the first dive at 40 meters went to the Lightning P-38, and then the second dive went to the Le Proté. So let me show you just a very short video about the diving on Le P-38. So now we are going to, so these two images are the images you see from the eyes of the robot. But when I'm looking at them, I have we merge them together and we see them in 3D. So here the robot is approaching the aircraft, and we're going to be able to touch and feel. I'm going to put the sound because forward, down to the right, back forward. Slowly, we're almost there.
Your hands on the
In the back, I have to come from the back to rest. Okay, I touch it, I feel it. Yeah, I mean with the back of the hand. You can feel it, put your hand, you can feel it. You feel it. You can see the hands deforming, and you can feel it. It's amazing. You see it, and you are able to feel the contact. That was really, really incredible to experience. Then we went to Corsica. Now that happened really later because there were some problems with the boat. We had to wait until February. So in February, we were in Corsica, and we went to Aleria. So Aleria, this is the site of Aleria, wonderful, incredible site with archaeological artifact, incredible site with so many things. The boat actually, in fact, disappeared because it was completely eaten by the biology in the water. And you can see here the catching of oil lamp. You see the oil lamp in the hand now. It was amazing. So quickly you get the oil lamp and you place it in the hand, and now we take it all the way to another robot that is holding the container for it. Then we went down further to another area where the crispy is, and the crispy was found only in 2015. It is a site that is just amazing. I cannot describe how powerful the emotion you have when you reach the crispy. This is the robot on the crispy placing a mirror to do photometry. So you see now we succeeded to place the mirror, and this was done by going down to 500 meters, approaching the boat, and the boat was broken in two pieces. You can see here the crack on the crispy. Let's see how we touched it. I mean, when you touch it, you're feeling, you're very careful not to, and you see these colors, and then, oh my God, now you turn to the left, you turn to the right, you press, and for a moment we were not able to open the hand, but then fortunately we fixed it, and then the hand was opened, and we were able to place this mirror so that we can do the telemetry. So you can see now the mirror is in the image, and now we can reconstruct the 3D image of the boat, which is incredible. There is a lot of wonderful images there, but also it is a sad sight with all the people who were lost on this boat. Now, let me show you a little bit of the colors around the boat, and also the images of that area where there is the crack. You can see this crack. In fact, we are reaching a bathroom here, and touching the structure, going to touch up a little bit, and you can see how immediately you avoid, avoid the corals. We don't want to disturb anything on the boat, and that was just unbelievable. The all those emotion you have, being there, able to touch, and at the same time you are feeling the contact, and in a place that is so deep behind you, under the boat where you're operating. It was incredible. Then we took the robot to the area closer to Nice. There is an aircraft at 68 meters that has well, everyone survived on when this aircraft was lost. But here you can see the idea I talked about earlier, which is to have this camera and light that allow us to now go inside the enclosure that where the robot cannot go. So we approach the door, and then we place the camera inside. You notice that one hand is rotating the bar so that we can rotate the camera, and you can see the camera now here, and it's going inside, and you can see the motion with the camera. This is an amazing thing also to do, to be able to reach inside areas where the robot cannot go, of course, but now we are able to access and film and see what is going on inside. So here is the robot going. This is from the eyes of the robot. You can see the robot approaching the door, and now it's going to put the light. So here the light on the windows, and now we're going to take the light to the cockpit, and you're moving inside and reaching to those hidden areas. Well, then we took our robot and we went deeper because we wanted to test whether this robot can really go to the depth. And we didn't know, but in front of Cannes, the Cannes Festival, there is a cliff in the water. So we went down to 750 meters. And at 750 meters, we were reaching like the bottom, so we decided to move further and then kept moving. You can see the robot is holding a plaque, and the robot kept going to 850 meters and kept moving down and down and down until the robot reached another bottom. And at that point, we decided it was like really late in the night, and we decided to stop. And but this plaque collected a lot of the sand from the area around the bottom of the sea. You can see the sand here. Let me show you this more. You can see all the sand that we touched and brought back. And the plaque says, "A robot's first touch of the deep sea floor, a vast new world for human to explore." And that was the price of Palme d'Or for OceanOne. That was brought by a lot of people who were so excited, so happy to see the success. And that involved the crew, involves scientists, archaeologists, and my students.
Yeah, congratulations. It's very amazing. And it's very amazing and captivating to see all this mission and history. I think it's something. Yeah, I'm just speechless. Again, I think what's really interesting about the design, I think maybe I want to ask you in this iteration of the design, it seemed the material part and going to 800 meters is deep. So can you tell us about the sensing and the hand development, as you mentioned, cooperation with Pisa University, being deformable and compliant, and also the sensing here, the haptics, and also the material part in the design. What is significant part of the design, Professor Oussama, when you try to see all this over the years? What was most significant part in the design of Ocean?
So as I said, really the challenge we wanted to address is how we can take hands to the water, to the depth, deep in the oceans. And in fact, there are very rigid industrial arms like the shelling arms and others that are really strong and capable of operating in industrial setting. But for many of the tasks that we wanted to do, we needed a compliant arm. A compliant arm is not built in titanium or built with very heavy metal. We had to build it a light arm to make light and safe contact with the environment and with divers, and to be capable of performing dexterous manipulation. So this is the challenge. How can you build an arm and attach it with a vehicle that is capable of operating all of that autonomously, together with all the visual feedback, stereo and sensing and all that information. So building robots that like if you take a spherical shape or cylindrical shape, you just put the metal and dimension it to sustain the pressure. But when you have an arm, then you are dealing with something that is going to be very fragile under the pressure. So the only concept that you can imagine is to bring some liquid inside that will have the same pressure as outside. And this regulation that we have, this compensator, is taking the pressure from outside. Imagine like you have a spring and it is deforming with the pressure, and it is pushing the oil, the liquid, inside that tubing to go and have the same pressure outside. So you're fine. And that from the design point of view, connecting all these links, because you have multiple links, so you have tubing going between the links, that was really challenging. And thanks to our collaboration with Mecha Robotics, we were able to do that. But then when we went deeper, we were facing more problems with the electronics and the redesign of everything so that we can sustain much higher pressure for the electronics. Now, the robots like this cannot be heavy without having huge thrusters. Then you're going to have to lift the weight. So what you do is you want to build the robot to be like floating, like in space, but at the same time floating with the ability to resist the pressure. So this is where the problem of flotation becomes really difficult, because if you go deeper and deeper, your material flota is going to have to sustain that high pressure. And what we were able to do is really like what is happening today in robotics as a whole, is that we are really lucky to have a new material. There is a whole convergence of technologies that is enabling us today to build robots in ways that we couldn't do it before. So this material is light compared to anything that we had before, but at the same time is going to be very strong to sustain the pressure in the water. And in collaboration with a company actually in France, we were able to design. It is very complex design. You have to make sure all these cables are routed in the proper way inside those flota. And finally, as you can see, the robot became really, I mean, almost perfect. You don't see any cable, but there are so many things going inside. And all of that, was really challenging. Now, I don't know if you notice, I mean, I just show you a very short clip of things. The robot head moves and always follows the hands, so that you can see your hands with respect to the environment you're manipulating. You have a lot of sensing and ability of control. The robot is autonomous. The robot is interacting with the environment. We can tell the robot just go to that location. But the problem in unstructured environment is that you need to connect the robot haptically to the human. So the archaeologist, the diver is able to dive through the robot. So to do that, we have 7 degrees of freedom haptic devices that allows you to grasp, allows you to manipulate position and orientation. But these are only attached to the hand. But the robot has many more degrees of freedom. So there is this redundancy that is used to be combined with what I talked about in the beginning, macro-mini coordination. So everything is taken care of by the system itself. You can just focus on your hands, and the robot is dealing with the constraints with every aspect of the manipulation and the navigation without the human intervention. So the robot, in a way, is your sensor. The robot is responding and asking for help, and you're helping the robot. So you're able to interact with the robot in that way. And I should say, this is not only for underwater. I mean, we don't have too much time, but I could show you how we are using this in construction, in the medical field. We are able to do ultrasonic imaging at 10,000 kilometers now. I mean, one of the things I would like to do in the future is to have this robot diving and have a school student, university students interacting with the robot remotely from their laboratories equipped with haptic devices. And I think this is possible. I mean, all the technology is coming together. Uh, I really think the next phase in July, we are going to have another expedition, and there will be more uh, complex tasks that we will performing. We are going to focus on the marine biology and bringing samples, and this is very, very challenging because the fragility of the corals involved. So it is very exciting, and we keep raising the bar. And as we say with my friend Bruno Siciliano, we are keeping the gradient.
It's amazing. We want to ask you what maybe still missing from your vision and these expedition. When you look for robotic field, maybe this is will push forward, maybe in the sensing, maybe in the design, dynamics. What is the missing piece you think that we can make the robot more autonomous beside the haptic, the senses, which is really amazing to touch what is happening in the in this deep level. But what's missing, do you think? And you think that will be pushed forward?
Well, I mean, there are a lot of things we are working on, like SLAM underwater. We have, in fact, cameras looking down and looking at the environment, and we are testing this in the pool, and we are very successful in the pool. But when you go to the real field, there are a lot of things that come. Even if you keep station with your SLAM cameras, there are a lot of currents that can change completely the configuration and the setting, and changing the ground or changing the position of the robot. So the intervention of the human is important. I mean, I insist that in unstructured environment, being it on land, in space, underwater, we need the human to be connected. Autonomy of the robot is always increasing, but you still need even to feel, because you need this connection. Even if the robot is autonomous, you want to see what the robot is touching, whether the surface is really stiff, resisting, whether this object is broken, or I mean, you need to touch. And at the same time, you are given the opportunity to make corrections, and there are some cognitive decisions that cannot be handled by the robot. I mean, the autonomy of the robot ultimately is, let's say it's just functional autonomy. The full autonomy is not there yet, especially the cognitive autonomy is not there yet. And there are a lot of decisions that needs to be done by the human. I mean, we know we don't want to be operated minimally invasive surgery without a surgeon. We are doing minimally invasive surgery in the water, but you still need the human expert to be there. And I really believe this is going to be for a while in terms of supporting the robot. As we increase the autonomy and bring more cognitive autonomy, we still need it at least to feel what the robot is touching, what the robot is doing. But what is going to be really important is to think about the capability of the robot to be without tether. So that technology is developed. There are now optical modems that can be used. And once we have that, then we will have multiple of these robots working together at the level bottom of the sea. But then above, you can have a relay station where you are communicating with these robots, because optical modems works for 20 meters, maybe less or more depending on the water quality. But then also the biggest problem is autonomy of power, the power autonomy. So you need to be able to have a relay station where you can recharge these robots without having them coming up if they are without tether. So So this is something is going to come, where we are going to have power communication with these robots in the water at depth, working together in cooperation. Water doesn't let you use electromagnetic signals, so we cannot. I mean, in a way, water is much harder than the air or the space, because well, in space you have radiation, but there you have uh, no signals, electromagnetic signals, and you have also the problem of moving water when you move your hand and arm. So the dynamics is different. You have to account for the hydrodynamics. You have to. I mean, there is a lot of challenges that we have to deal with, and now we are dealing with more challenges related to how we can bring more capabilities to operate for extended time underwater uh, through the addition of supporting relay stations and other robots.
Great. Maybe I will go for a question from the audience. The first question, hello, Professor Oussama. I'm CSC student. It's hard to find roadmap to robotics field for people who want to learn in the field.
So the question is how to get into robotics, right? Well, this is a really good question. Thank you for this question. Um, Actually, I don't think it is really hard, because robotic is multidisciplinary. So whether you are studying in humanity, whether you're studying in the medical field, whether you are doing mechanical engineering, electrical engineering, computer science, you are able to contribute to robotics, because really robotics brings all these domains together in a system that requires a physical embodiment, but at the same time it requires design, control, and in the applications we have all these issues, but also we have all kind of ethical issues we need to deal with when we use robots, and we need to understand more about the human, so that we can interact better with human. So I really think it is the doors are many and the roads are many and converge to robotics. Now, when you start your study, one of the things I always advise those who would like to get into robotics, in the robotics field, is not to skip the foundations. Physics, mathematics, and computer science. If you get these, you can get into robotics very easily. And getting in the field is becoming uh, even more and more needed. I mean, at ICRA this year in Philadelphia, we had almost 8,000 participants. I recall the time we were aiming for 1,000 in the year 2000, and we get more. Actually, I remember 1,700, but now we are coming closer to the 10,000 at ICRA. So the field is growing. It's very exciting times for robotics, and robotics is really here with maturity, coming from all the years of study that we devoted to robotics, but also by the convergence of technologies that are enabling us to build different, more advanced kind of robots, like what I always was looking for, which is the dexterous compliant robot. It is not anymore just the heavy, precise industrial robot. We are talking about robots that are light, capable of dexterity, and capable of assuring safety for the interaction to people interacting with them and to the environment.
Thank you for that. Also, question: if you could solve one problem in robotics, what would that be? I think it's like.
Well, the problem is there is not one problem in robotics to solve and fix it. So in robotics, we have large amount of perception needed from sensors. We have a large amount of action needed by the robot. And today, what we are really facing is the fact that we are very often connecting perception to action at the very low level of control and of interaction, so that it requires a lot of programming, challenging programming, which was okay when we were working in structured environment where we can put fixtures and jigs and organize everything. However, today, when we say we are taking robots outside of manufacturing to help human to be interacting, supporting domestically, in the field, in all these different environments, the challenge is who is programming these robots? And the only model we know about creature who can really interact with the real world are human. So how can we learn from human those skills, and how can we bring those skills and encode them for the robot? So I really believe the next phase of development in robotics is going to bring more and more effort to abstract the programming of the robot from trajectories at the joints to a higher level where the robot is autonomously capable of performing those skills. So skills in manipulation, in navigation, in interacting with human. And the domain of machine learning is growing. However, the learning I'm talking about is how we can encode these skills, which means that we really need to remember that we have a physical system that has physical models that describe the behavior, the extent of stability, all the aspect of the system, and physical interaction, observing the human. We need to understand what's going on. We don't want just black boxes. We need to understand. So from data, we need to go to the stage of understanding and taking those capabilities that we observe with the human to new capabilities for the robot, which is different. Robots has fast dynamic responses. They close the loop at kilohertz. Human are much slower. Human, actually, we use prediction in our interaction with the world. So we need to realize that and encode these strategies for the robot. These strategies are amazing. I mean, once you start working on observing a human, how we perform these complex tasks, well, this is something that is very hard, and we have been working on it, and we will continue to work on it all together.
Awesome. Also, another question. What is your opinion? No, first, there's a question. Before, when we expect soft robotics will completely replace conventional robotics? I think in the part of you mentioned the deformable hand, but I think it's a generic question. Your thought about soft robotics will complete. I don't think. What do you think of this question?
Yeah. So today we talk about soft robotics, and soft robotic is developing and making a lot of progress and success. But let me say something about the fact that we are not talking about one modality of robotic system. Soft robotic will not replace the other needs. Human bodies, we have the skeletal system that is supporting the soft skin around it, and in many tasks we need both. So how do we do that? Soft robotics can solve specific problems that do not require the stiffnesses that are needed in other tasks. So we need all these different fields to be together, and we never say this or that. OceanOne is operating on the physical world, but around it you have a lot of vehicles, and all of these are part of the team that is going to work to accomplish complex tasks. So please do not try to say this is the solution, this is only the way. We should not say, oh, machine learning is going to solve everything, or we don't need the machine learning. Yes, we need machine learning. We need all the technologies that are being developed, but we need also to use all the models we have. We need to be really wise about how we bring all these foundational development to building robots that are capable of doing all the different things. Robots has to be versatile, and robots can only be versatile by really integrating capabilities similar to those of a human. They are not human, they will never be human, but those capability of versatility are very important, and teams of robots can work together to bring different aspects of that versatility.
This is an excellent point. There's a question. Can we ask it? I don't have time or not?
Yeah, I'm fine. I'm fine.
Okay. What is your opinion in model predictive control for fast mobile system applications such as drones?
Yeah, of course. This is very important. In fact, not only for drones, for running dynamical system, these are going to be more and more important as we go from walking to dynamic walking. And as we develop those advanced techniques, we are going to be able to bring in new capabilities to the robot system. So I think robotics now is growing, and a lot of techniques that comes from the control theory, or sensors and actuators that come from mechanical design. All of these are converging and bringing new ideas and new capabilities to our robots, and we really need to realize that these capabilities are going to increase, because today the embodiment is improving. We are seeing the robots with torque sensing, which means that now we can build safer robots, more compact, lighter robots. We see the progress with soft robotics that is enabling interaction that are also safer and more effective. But all of these will bring together systems that we haven't seen before, and it is really exciting times for robotics.
Mm-hmm. So the question left, in your opinion, what is the biggest current challenge in mobile robots path planning?
One of the thing about motion planning is that motion planning for robots, mobile robots, is really not the biggest problem, because the number of degrees of freedom involved are much smaller. I mean, the complexity of motion planning grows exponentially with the number of degrees of freedom. So the problem is, once you have arms with 7 degrees of freedom, you have multiple arms, you have the body, you have self-collision, you have... Now the motion planning problem, configuration space, see obstacles, becomes really difficult to compute in real time. But even for mobile robots, if we think about planning only, planning is some sort of trajectories that come from an instant of understanding of the environment and knowing where the robot is and where the robot is going. But in a dynamic environment, in an unstructured environment where you don't have access to all the object in that environment, you will advance, and then you have to move again back to your planning and replan again. So one technique we developed over the years, starting with elastic band and elastic strip, and I'm not sure if your auditor are familiar with this, but maybe everyone is familiar with potential field. So potential field was the idea I proposed many years ago, which is to create reactivity. So you react. Now, if you react, you might, with potential field attractive and repulsive, you might get in a local minima. So what we decided to do is to think about a plan, a trajectory that you're planning, as a physical elastic that is going to deform under repulsive and attractive potentials. The attractive potentials are things that we artificially create on the trajectory by creating tension, so you get a smooth and shortest trajectory. And for the elastic, you start with your initial plan, and as you move and you discover and see and perceive the environment, you are going to deform it. So this was done back in the 90s and was advanced by later to be implemented in the real world. Instead of configuration space, we went to the Cartesian space, and this idea was further developed with strategies around it to deal with the homotopic behavior of the deformation and the elastic planning. So think about elastic planning, and elastic planning is an amazing way to keep your plan alive, corrected, updated, reactively.
Mm-hmm. That's a great. Maybe a quick question here. If there is any critique or disagreement regarding maybe the approaches for solving this problem, for you, do you think there's maybe, you disagree with other approaches or critique, or you don't have?
Well, I think every one of us is contributing to advancing the field, and we have to be open to all the different ideas and try to see how these ideas generalize and how these ideas work. And there have been so many great ideas in the field and contribution, and that's how the field has advanced. So I really believe an important characteristics in robotics is not to come and approach robotics from one point of view. I'm mechanical designer, and I really think about it just from my own point of view of the sensor I'm placing, the actuators, and or I'm in computer science and I'm going to just look at digital information and data without looking at the physics and the dynamics, or from control point of view, or from any other point of view. We have to be really open. And the success in robotics comes when we start opening our mind to every different idea and evaluating it and seeing how this idea works. In the beginning, my work was always based on an approach to think about task-oriented control. And it's a little bit like human focus on the task. I'm reaching with my hand. I'm just focusing on my hand to move, but my shoulder and my body is adjusting autonomously in the background. And then there is a sort of collision avoidance that is happening in a very reactive way as I'm moving around the object and moving my hand between those objects. So in the beginning there were all kind of discussions, all this is this way or that way, but ultimately everyone realizes that actually all the different techniques converge towards some unification, because task-oriented control might integrate every aspect of joint control. That is, you are basically defining your task in that way. So whatever your definition, and then you can extend those ideas to many other techniques that were developed in different contexts. And this is, I think, very important for us to have an open mind of collaboration between the different disciplines that is contributing to robotics. And I really think this is the only way we can move robotic forward.
Amazing. Maybe since the close end, a few questions. I'll take one question from the audience. Where do you think the research in robotics should be focused more nowadays? Software or hardware? I think it's related to embodiment, what you mentioned, the brain and body. Which one I think, yeah, yeah.
So, so for as I say, for many years we were fighting with the robot rather than doing the research. So the robots didn't have all the capabilities. I mean, we say we want to compensate for the inertial forces, but there was no real control of the torques. So you need to really be able to control your torque and overcome the friction and nonlinearities so that you can compensate for them. And those robots were 99% of robots by the 21st century were just position control. And from the mid 90s, we were developing torque control, and we were talking about how important it is to allow us to create dynamic control, high performance, but also to interact with the physical world, to touch and feel and control those systems. And this technology started to happen by the turn of the century, and it came from labs. I mean, our lab, DLR, and later transferred through KUKA, and then we started to see other companies, younger companies, starting and bringing those technologies. So now I feel the lack of good hardware that allow us to really explore robotics is here, and it is happening. Some industries still close their systems. They are not open so that you don't access the low level of control, and we are complaining about it for ages, from Unimation and to more recent development. But I think manufacturers started to open up and understand the important role of opening their software so that we can access really their hardware systems. So sensors are being developed. We see a lot of development in tactile sensing, in miniaturization of force sensors, and in a lot of additional sensors of that are coming. The vision is being integrated. We have like revolutions in miniaturizing cameras, and we are able now to have cameras in the hand of robots. And so all of this is really what I said earlier, the convergence of technologies, hardware technologies that are bringing new hardware, but also we are seeing faster computation power that is enabling all these things to really work in real time. But what is happening is we still have our old habits, and our old habits is that we are used to program robot joints to create trajectories, synchronize these trajectories to move, and this is not the natural way of controlling robots. So we need to take advantage of the new capabilities that is being offered to us, like to go further and bring algorithms that take advantage of the torque control capabilities of the sensors of all of these things, and stop just locking the robot joints, arms, trajectories to move along pre-programmed, specified trajectories. So this is something that is happening now. We realize hardware is here. Before it was software and no hardware, so it's a cycle. There is this cycle that we develop new hardware. We need to bring new algorithms. And new algorithms will point to the new directions in the hardware. And I think this cycle is accelerating, and it's really a beautiful thing.
Maybe a quick question for Oussama on the point. I think that's really excellent point. But maybe I want to ask you about the way of the choosing the solution or approaching the problem. And do you think it's sometimes, I don't know, where do you see the solution? Because what you're doing seems so maybe not really traditional. I mean, it's a little pushing the envelope and maybe risky. I don't know if you, maybe I'm wrong, but that's from my limited perspective. But it is, do you think in general robotics field there is much push to go for, let's go for the edge and just push here, as I perceive what you do is very, in that case, risky and pushing the envelope. So in robotics, where do you see the problem lacking this, to approach a problem or think about solution, the way you think about the problem and solution?
Yeah. I mean, in robotics, we can think about an algorithm, and we find it a little bit complex. Then we add one sensor, and we change the problem. We can have a problem and develop those algorithms, but we take another look at the representation. We change the problem. So robotics is very rich, and it lets you be really creative with the way you approach problems. Don't rush to use just like the textbook solutions. We have to think about what we are doing. We have to think about the way it is implemented. I mentioned we can now control robot at 10,000 kilometers. This is in answer to the question about teleoperation. In teleoperation, we have one loop. Delays immediately make the robot unstable. I mean, as you start putting delays. So the solution we brought, which is called the dual proxy distributed autonomy, is essentially to have an autonomous robot in one side. So you have one loop here, and another autonomous haptic device on the other side, connected by an intelligent interface that communicate what is needed so that you can perceive and you can operate. And that changes everything. So it is the same problem, but you reset the problem differently by thinking about other solutions. In fact, in robotics and in our field, I think the most difficult thing is to come up with the problem to solve. Solving the problem is always easy, but finding the right problem to solve is the most difficult thing. And very often we go and solve not always the most important problems.
That's very fascinating. Excellent point. Yeah. Maybe one question left. If there is something where we would like to change in the ocean robot, since you still have in July another and you try to raise the bar, but if it's something you notice that you would love to change in the, I don't know, if there is anything when you think about it, maybe change this aspect?
So for OceanOne, we just changed the robot dramatically from the first original version to what we have now. As I said, the next step is going to be a step where now we bring power autonomy, and that is technology. It is really how we can build a sort of transition station at seabed or above, where robots can now recharge and continue working on the cable of the internet underwater, repairing them, or building and fixing and monitoring structures underwater. The operations that we are talking about, I mean, divers, when they go to 60 meters is like fine, but when you go to 100 meters, it's becoming harder and you have shorter time. Then maybe some rare divers can go deeper by using a mixture of helium and oxygen, because oxygen becomes toxic as you go deeper and deeper. So the problem is there is no other solution to exploring our planet. I mean, it's just like incredible that until now we haven't seen these oceans. We know much more about the moon and Mars than maybe our own oceans. So it is really a serious and challenging problem. We can have all these submarines going down and looking, we can see it, but can we bring samples properly? Can we build structures? Can we place sensors? And can we interact with that environment without some sort of artificial divers? So we really need to be able to interact with the physical world in the seas. And there are so many resources, so many artificial structures that we need to build, and so many natural environment that we need to help. All the things that go underwater, we have little knowledge about. So I would imagine we will have many stations with many robots working together. And to do that, we need to add a lot of supporting equipment and systems that allow this robot to stay, and they can stay for a long time and operate for a long time. So I think this will happen eventually. This will happen, but it is going to take a major effort to really move to that level where you can have a stationed robot operating and working and connected easily to human on land.
That's very soulful. Maybe the last question.
You keep telling me the last question. You keep telling me the last question. I'm enjoying it. I'm not complaining. I mean, just but
It's a last
go ahead.
question, promise. It's a last question. Maybe since you have the over 30-year experience, Professor Oussama, I'm curious about what really, in the way of thinking, change equality, or you have witnessed robotics in more than 30 years, and that's fascinating, and many people really grateful for your courses, and that's for out of discussion. But I mean, what's actually in your mind changing in all these years you have witnessed all these things? What is the most important thing maybe changed in you in the way of thinking?
So you start with a vision, and you start with an understanding of your understanding of robotics. So robots are the implementation of robotics. Robotics is the science around all these systems that we are building. And you have a vision and you start working on it. But of course, the technology is not ready. And I always overcome that problem by never thinking about the limitation of technology as an impediment to keep your vision and move forward. So yes, maybe we don't have those light actuators. Yes, we don't have those sensors. I would say they will come. So when they come, what can we do? And this is different from the problem of really going to engineer a solution that is going to be used immediately. So looking at the field, where we want to take the field, and what are the frameworks, architectures we're building, and how we can build them. So very often we look at problems and say, oh, I mean, these are the limitation. My battery is limited by this. My computer is limited by that. This shouldn't be at all, at any time, a reason to change your vision. And I think if you have that vision and you work towards developing, proving the vision, there are always ways of demonstrating your vision, even if it's not uh, with the full capabilities that you want to see in the hardware or in the computational tools and all of that. And I think sometimes I notice that we just say we think, well, computers are give me this uh, speed in the servo loop, and my sensor is this big, and my motor is that large, and that's it. And I'm now constrained by all these limitations. No, we can do better. We can imagine the new robot and prepare for it.
That's really powerful. Powerful. Maybe I don't know if you have any final words like say for people listening or robotics community. Any final words like say?
Well, thank you very much for this opportunity. Robotics is a fascinating field, and uh, as I tell my student, uh, all this journey, I feel I'm still doing my PhD in robotics.